Hey Mustangs, in this video we're going to be taking a look at population genetics with a specific focus on variations and gene pools. So first we're going to start with variations, and that's going to help us understand gene pools a little bit better. So one of the biggest things in order to get what's going on with variations is to understand the bell curve. Okay? If you were to gather all the individuals of a single species in front of you and line them up, you would find that there is variation for just about every single trait that you can see in that species. So there's always going to be variations, differences from one individual to the next within that species. Now, as you look at those traits, you'll find that usually for most traits there's going to be an average where most individuals within that species have that version of the trait. So let me give you an example here using these crocodiles. Okay, so when you look at a bell curve here, what we're seeing is on the y-axis, this is the number of individuals. So the number of individuals that represent a version of that trait. And down here on the x-axis, this is going to be the variation of a specific trait. So using these crocodiles here, I'm going to say, in this case, let's say size. Okay, so down here, this is size. Now, if you were to gather all the crocodiles together, you'd find that most crocodiles fall into a certain range for size. So let's say here, let's say this is like 12 feet. I'm just making this up, okay? So I don't know for sure. So let's say this is 12 feet. Let's say this is 11, 10, 9, is 13, 14, 15 feet, okay? Again, this isn't scientifically accurate here. I'm just giving an example. So let's say most crocodiles fall into the 12-foot range. So you see that there are more crocodiles. So if this is the number of crocodiles, there's more crocodiles that are 12 feet than anything else. As you go away from 12 feet to the left, as you get smaller and smaller, you find less and less crocodiles that are that size. As you go to the right, you find less and less crocodiles that are this size. Now you should be asking yourself, why is that? Why do most crocodiles fall into the 12-foot range? Well, we can connect it to what we learned about natural selection. Those with the best traits are more likely to survive in their environments. So something that has to do with size, being this size is best for the environment. As individuals move away from that size and you find individuals that are smaller, maybe being smaller is not a good trait to have, so you find less and less of those individuals in the environment. Same thing as you move away. Maybe being bigger isn't good, so as you move away from the 12-foot range, being bigger means less likely to survive. So basically what we see here is that most individuals will always fall into the average range because that is the best of the trait to have right there. So there's a crocodile, so we used our crocodile example. Same thing can apply to humans though. There's always variations and a range when you look at people. And think about human size. Okay, so human size here. So here is the shortest man in the world. Here's the tallest man in the world. Here's a picture of them. Shortest man is a little under 2 feet. And tallest man is a little over 8 feet, about 8 feet 3 inches. So if we were to draw a bell curve for this, okay, so you do your y-axis, your x-axis, and this would be height here, and this would be number of people at each of the different heights that we see. So if we were to gather all the humans in the world, we find that starting with this man, the shortest, there's no people that are 0 feet tall. Okay, so 0 feet, they're not there. But as we get to about 21.5 inches, which is this guy here, the shortest man in the world, there's one person that's like that. There's a few people that are around 2 feet tall, more people that are 3 feet tall, more people that are 4 feet tall, more people that are 5 feet tall, and most people, if we were looking at humans as a whole, would be between probably about 5 and 6 feet. So let's say this is 5 and 6 feet right here, between 5 and 6 feet. And then as you go past 6 feet, you find less and less people that are like that. So less people that are over 6 foot, less people that are 7 foot, and then finally you get to the 8 foot people like way down here. Okay, so right here is the range. This is where you find most humans are. Most humans fall into this as the average. So there's more people that are there than down here. So there's less people. Here's the 2 foot people right here. And you can see how humans fit into the bell curve. All right, so reasons for variations. It comes down to this right here. So mutations can cause new alleles, and that can lead to new variations. And then there's sexual reproduction. So with sexual reproduction, this explains variations within even a family. So if we look here, in sexual reproduction, crossing over during meiosis causes a mixture of different traits that didn't exist before, so you get more variation. Independent assortment, during meiosis, the way the chromosomes separate out into the different gametes is going to cause variation. So each gamete is going to be a little bit different from the same person. So from one person, their gametes are not all the same. And then fertilization, same thing. Since there's different gametes, different possible combinations from the male and the female, that leads to variation. So they're not all the same even within a family, unless it's identical twins. And then identical twins, of course, that was 1 sperm, 1 egg, and that's different in that case. All right, so a gene pool. A gene pool is all of the different alleles from every single gene together for a population. Now, gene pool is important to know and understand because if a gene pool becomes isolated, then that can lead to speciation. So a gene pool is all the different alleles from all the individuals for every single gene, like we see here. I kind of like this one a little bit better. So this is the gene pool from every single individual from the entire group. This forms the gene pool. Now, if a small group becomes isolated and they separate from the rest of the gene pool, that leads to a potential of speciation. So now you have a different gene pool here. So imagine we took a small group of these and we have here, we've separated, we've isolated them. Well, now that they have been isolated, now we have 2 different gene pools. And if there's not going to be any gene flow between them, like they're not going to immigrate and emigrate between the 2 gene pools, then that means this can change and become different over time. So whatever individuals are in this group will change and become different. And over here, any individuals can, in this group, change and become different over time and lead to speciation. All right, so allele frequencies is how often an allele occurs within a population. So here is a gene pool, really simplified gene pool. And if I asked what are the frequencies for W dominant allele and the recessive allele here. So there's 24 W's altogether. So in order to calculate for the dominant allele, there's 4 dominant alleles divided by 24. That would equal about 17%. And if you did the other one, 20 divided by 24 for the little recessive allele, you'd get 83%. Okay, so that's the allele frequencies, how often an allele occurs within a population. Then you have genotype frequencies. Now these are super, super important to get, especially when you're talking about Hardy-Weinberg. So the genotype frequencies tell us the percent out of a whole population. If you gathered all the individuals of a population, what percent of all those individuals is homozygous dominant? What percent of all those individuals is heterozygous? And what percent is homozygous recessive? That's the genotype frequency. So it's telling us how many of all the people are each of these types of genotypes for a given gene. All right. So as I just said on the previous slide, Hardy-Weinberg equilibrium. So in order to calculate Hardy-Weinberg, we have to understand Hardy-Weinberg equilibrium. So Hardy-Weinberg equilibrium is a condition in which a population is not changing at all. So you have to ask yourself, what would it take for a population to never change at all? And if a population is never changing, that means that the allele frequencies and the genotype frequencies will never change either. So these are the 5 things that it takes for a population to never, ever, ever change. So the population has to be large, so that way no genetic drift can occur. There has to be random mating. There has to be no mutations. No gene flow. So that means no individuals can leave and no new individuals can come in either. So no immigration, no emigration. And of course, no natural selection, because we know that's a driving force for change right there. So no natural selection. If even one of these is not met, then that means a population is evolving.